Hi guys, and welcome back. Mr. G here. We now going to wrap up this talk on the gradient by looking at some interesting observations. Okay, we have established how the equation of a straight line looks like in general, and we kind of know how to find it because we know we will always use the gradient. But of course, for a full detailed explanation on how to go about that, we will do that nicely under a separate topic of functions. Okay, so you can tune in into that if you really want to get the hang of this. What is really important in this analytical geometry talk is the distance formula, is the midpoint formula, and that example that I gave, and finally the gradient formula and how gradient of certain lines behave. Okay, so I'm going to start with parallel lines here. Okay, I have this line here, line Rn is parallel to a segment, or the line segment DLE or DE, whichever way you want to call it. And I also have line segment here, GH or GMH or HMG. Okay, it's really up to you. Parallel to line. Now this one is a line because it has not starting point or end point, but it's a line with 2 points that are defined on it, Q and O. So I want us to observe what happens to the gradients of these two lines. Here the coordinates of Q 18 and 0. Here the coordinates of O 21 and 2. Here the coordinates of M is 19 and 3. The coordinates of H rather here is 16 and 1. Okay, so we said gradient is basically change in y, the ratio of the change in y over change in x. Let me quickly ask a question. What is the direction, or yes, the sign of this gradient? Is this an increasing slope or a decreasing slope? Okay, and in other words, what do we expect m to be? We expect m to be greater than 0 or less than 0. Okay, I hope you have the correct answer and you have said it. We expect m to be greater than 0 because this is positive. Okay, so we're going to figure now we're going to figure out the change in y. Let's take the simple segment. Well, we're going to take both of them. Okay, we're going to take both of them actually. So yeah, that's I think that's proper. Let's go through that. So this is the gradient of, let's look at HG here. Okay, we know that HG, the points HMG are collinear, so the gradient of HG will be the same as the gradient of HM. But so that you are satisfied, your doubts are satisfied, let's go for that. Let's look change in y. Let's start with change in y. Remember, y here is 5, okay, and y here is 1. So the change in y is 4, okay. So now 1, 2, 3, 4, and we are at G. Good. What about the change in X? 1, 2, 3, 4, 5, 6. The change in X seems to be 6, which will be 22 minus 16. 4 over 6, we can write this as a simple fraction, right? Because 2 is the highest common factor between these two. So 2 goes twice there, goes 3 times here. So that's the gradient. And as we had said, this should be positive. It is positive already, so we don't need to put in that plus sign. So let's study also the gradient of this line OQ or QO, okay? QO, again, change in y over change in x, and we note that we expect this thing to be positive, okay? Very important to note. And let's go ahead and study the change between those points. Let's see point O and point Q. The change, as you can see, it is just 2. Let's look at X, 1, 2, 3. The change is just 3, 21 minus 18. And guess what? These things are actually equal. So here's an important fact. So we have established that M for HG is 2 over 3, which is equal to M for QO. We have established that gradient for parallel lines, HG, parallel to QO. The gradient for parallel lines are equal. In the previous video, we established that the gradient for this thing was 3/5, and we know it is negative because it is a decreasing slope, okay? Now, I'm telling you now that this line is parallel to this line. Without calculation, I can conclude that actually the gradient of this line, Rn, should also be minus 3/5. And I'm using the fact that they are parallel. One important fact as I close, we studied parallel lines and we just proved or discovered that gradient for parallel lines are equal. In other words, watch for this in your exam, guys. If the examiner tells you that the gradient of one line is equal to another line, you must conclude that those lines are parallel. Or if the examiner tells you the two lines are parallel, then you must be able to conclude that the gradients are equal. This is very important, especially when you guys have to prove quadrilaterals, that a quadrilateral is a parallelogram or that a quadrilateral is a rectangle, whatever the case is. It is important for you to know this property because you know in a parallelogram, two opposite sides are equal. Exactly, they are equal, and not only equal, but they are also parallel. Okay, that's one thing that you know about the parallelogram. So you can actually note that if you want to prove one of the properties of the parallelogram, if you can show that the lines, if you want to show that the lines are parallel, you can simply find the gradient of those two lines and show that they are equal. And you will then conclude that because they are equal, the lines should be parallel, and thus the shape should be a parallelogram. That is just a rough introduction to how you're gonna go through these proofs. Of course, I will cover that with you when we discuss a bit of Euclid geometry. For now, I'll catch you later.